Hello. So in this video, I'm going to talk about measurement, which we didn't have time for in class. And even before then, I'll sum up one of the example problems that we didn't quite have time for on Tuesday's lecture. So I'll talk briefly about the example problem and then dedicate the majority of the video to measurement. So the last thing we talked about on Tuesday's lecture was this. Total energy is a sharp observable for any stationary state. So a stationary state is a solution to the time-independent Schrodinger equation, and those solutions have definite values of total energy. So if something has a definite value, then it's if a wave function has a definite value of some observable, in this case energy, then that wave function is an eigenstate of that observable, and that observable is sharp. So if we were to measure that quantity, in this case energy, then we would definitely get a certain value with 100% probability. Right? So if you're like in the ground state of the particle in a box and you measure the energy, you're definitely going to get the ground state energy. So h bar squared, pi squared, 1 times 1 squared divided by 2ml squared. So there's another example that we didn't have time for. So I wrote up some of the algebra. It was actually calculating things with the wave function. So remember that so the main formula that we have here is to calculate the expectation value of any observable. So in this case, that observable is momentum. We sandwich it between psi star and psi. So we have psi star of x and the observable operator and psi of x. So in the case of momentum, we plug in the operator minus IH bar derivative with respect to x. And we can do that for either p or p squared. So for p squared, if you do this thing squared, you take a derivative and then take another derivative, that's the same thing as taking two derivatives. And then minus I times minus I is a -1, and h bar times h bar is h bar squared. So that's where for p squared, this is the operator for p squared. So then the rest of it's just math that you can double check. So the expected value of momentum is 0, which makes sense because you have a box and you have a particle in it, and it can't be drifting overall to the right or to the left. If the box is at rest, is in the box and it's staying in a stationary state. So remember, the probability density is not moving either. So it makes sense that the average or the expected value of momentum is 0. But there's some spread to it. So in the ground state of the infinite square well, you have an energy eigenstate. There's a definite value of energy. And so there's a definite value for the absolute value of the momentum. But the momentum could be positive or negative. Right? So we definitely know the absolute value of P, but it could be positive. It's 50% positive, 50% negative. So that's why on average it's 0. And that's also why there's some expected value for P squared. And actually, this is exactly equal to the value of P squared. So if you find the momentum so in other words, if you take the energy of the ground state of the harmonic oscillator and turn that into a momentum, and then square it, well, then you'll get h bar times pi divided by L, and then you square it, and that's where this comes from. So actually, you don't even need to do all this math because there's a definite value for the absolute value of the momentum. Okay. So one other thing, and the reason I wanted to mention this in the video is, so previously in this lecture, we derived delta x was this, the standard deviation of the x observable or measurement. So to compute that, we needed to compute expectation value of x squared minus expectation value of x squared, and then take the square root. So that's the thing in the red underline. And then combining these two ingredients for p squared and p, we can get the standard deviation of the momentum measurement, and plugging that into the uncertainty, or plugging it into this product, delta x times delta p, you get this value right here, 0.568 h bar. And that is greater than or equal to h bar over 2. So this is consistent with the uncertainty principle. And every wave function that you could possibly think of, if you calculate delta x and you calculate delta p, you'll get this. You'll get a quantity greater than or equal to h bar over 2. So in the ground state of the particle in a box, we closely saturate the inequality. We're close to h bar over 2, but not exactly equal to it. And actually, this gets worse and worse. You get farther and farther away from h bar over 2 as the value of n grows. So remember, ground state, this is all for the ground state. This is all these computations were for the ground state, the infinite square well. If you did a excited state, you would have a delta p that starts to grow quite a bit. And so this uncertainty principle will get bigger and bigger, or the delta x, delta p will get bigger and bigger, but still consistent with the uncertainty principle. Delta x is limited to, about half the size of the box. Okay. So completely changing gears to measurement. So there's a statement here that we're going to talk about all video. If you perform some measurement on a quantum system, the only possibilities you can measure are the eigenvalues of the measurement operator. So we have to know what that means, the eigenvalues of the measurement operator. What does that mean? So let's just say, so given an observable, some operator, right, with the square brackets, it's the operator. It could be it could involve derivatives. It could just be multiplied by x. So given the operator, there are special functions. There are special psi wave functions, and I'll label, there's several of them, so I'll label them psi sub n. There are several special wave functions psi n such that the operator acting on psi n is equal to a constant times psi n. So all of these are functions of x. Maybe I should make that clear. These are wave functions, and the operator on the wave function could give you a constant times the wave function again. It doesn't have to be the case. Remember, this is the difference between a sharp and a fuzzy observable. So what we're saying here is that every observable has a set of functions for which the measurement is sharp, for which there's a definite outcome of measuring that observable. So the eigenvalue is the value that you get out. So this is just a number or a constant. The eigenvalue is the result of that measurement. So for a position measurement, the eigenvalues are positions, positions along the real line. Okay, so in blue now, for example, if we measure the energy of any wave function in the particle in a box, so now our measurement operator is the Hamiltonian. And so if we look at this equation, we consider our observable to be the Hamiltonian operator, and then the eigenvalue, the thing underlined in red, the eigenvalues would be the energies of the states. And the collection of states are the stationary states that we solve for, the square root of 2 over n, or sorry, 2 over L, that's a normalization, sine of n pi x over L. These are the psi n, these are the eigenstates of the energy operator, or of the Hamiltonian operator. And the eigenvalues of this operator, eigenvalues, are the energies, right? So if you applied the Hamiltonian operator to psi n of x is equal to this function, then the value you get is n squared pi squared h bar squared over 2m L squared. Okay, so what we're saying here is that if you have a box now, so infinite box, and you have some wave function and it doesn't have to be a stationary state. So we had some rules about psi, but it didn't have to be, you don't have to have the sine or cosine, or you don't have to have the nice wave functions that fit in there. Suppose we know that the particle is pretty close to being over here. Right? That could be a valid psi of x. But it's not a stationary state, right? So what we're saying here is that if our particle actually had this psi, so this one right here, our particle is trapped in the box, and this is the wave function psi, and we measure the energy, what we're going to get is one of these numbers. Right? Now, which one are we going to get? We don't know, right? If this was our wave function, This is not an energy eigenstate. And so we don't have a definite value of energy for this wave function. So if we were to measure energy, we're going to get one of these values, one of the eigenvalues of the measure of the energy operator, the Hamiltonian. But because it's not a sharp observable, we can't say with 100% certainty which value we're going to get. Right? We can find probabilities of getting each value. And that's what the rest of this talk is about. How do you find those probabilities? Okay, so this one right here, so just to label the notes well, this is not an energy eigenstate, not energy eigenstate. And for that reason, if we measure energy, there are several possibilities for what we would get. Several possibilities. So there's not one value that we would get with 100% probability. Several possibilities, but the only possibilities, but the only ones are these values right here. This is tricky. You're confused right now. I don't blame you. All right, let's. So this is repeating kind of what we were saying. So here's another example. So again, I'm reading the thing in blue. For example, if we start off with the stationary state, so the n equals, with this particular stationary state, the n equals 3 state of the particle in a box, the second excited state, and we measure the energy, then we definitely know what value we're going to get for the energy because our wave function was a energy eigenstate. So if you're already in one of those special, if your wave function is already one of those special functions for your measurement operator, then you already know what you're going to get out of the measurement with 100% certainty. But if we have a fuzzy observable, so for example, energy for this wave function, back in this example, this energy is a fuzzy observable for this wave function. All right, so let's see what we're saying here. What's in green here. If we have a fuzzy observable, then there is no way to know what we will measure. So we don't know what we're going to get out of the energy measurement. And this is what's key and weird about quantum mechanics. This is not a statement of our ignorance. It's not that it actually has some value of the energy and we can't measure it. It's fundamentally there is no well-defined energy of the particle, right, for that particular example. This is not a statement of our ignorance. The wave function does not have a definite value for this quantity until we measure it. And as a result of us measuring it and finding this energy, we actually change the wave function by doing this measurement. So this is called wave function collapse, if you've ever heard the term. The act of measurement will change the wave function. And it will change it in such a way that the wave function, after you measure the observable, the wave function will collapse onto that eigenstate. So for example, if we have this state right here, and we measured the energy, there's a chance we would get E2, the energy corresponding to the state n equals 2. So the probability wouldn't be 100%, but there's some chance that we would get n equals 2. So if we got the n equals 2 energy out of this, then the wave function then becomes the n equals 2 state. So we've changed the wave function at that point. We've collapsed the wave function onto the n equals 2 energy eigenstate. If we measured n equals 2, if we measured n equals 3 for the energy, then we've collapsed it onto this energy eigenstate. So what we change the wave function to as a result of measurement depends on what we get out of the measurement. But the result of the measurement is forcing the wave function to be sharp in that observable. And that forcing it to do it is going to change it. I would ask for questions, but this is a little less interactive. So I'll keep going. All right, so the main question that remains is how do we know the probability of each possible measurement? So how do we actually calculate? So I said that maybe n equals 2 is like a possibility for what we would get out of an energy measurement here. But how do we know the exact probability? So the way to do that is to write the wave function as a sum of eigenstates of the measurement operator. And a lot of times this isn't obvious how to do this. And this is really getting into like upper division quantum mechanics is actually the process of how you go about writing it this way. And there's a lot of math and stuff behind this. I mean, the fact that every measurement operator you can write this way, you can take any nice enough wave function and write it as a sum of eigenstates times some constant. The fact that you can do this is related to some special properties of your measurement operator. It has to be a Hermitian operator. Let me give an example with this. Right? So the ground state of the infinite square well is psi1 of x is a. Maybe I shouldn't use a because it's square root of 2 over L sine pi x over L. Now, if we're measuring energy, that's great. That's the way we want to write it, and that has a well-defined energy. This function right here is not a momentum eigenstate. Right? If you apply the momentum operator to this wave function, you do not get a constant times the wave function again. Right? You take a derivative of sine, you get cosine. That's not a constant times sine. But, and the reason I chose this example is because this kind of works out nicely mathematically. If you can rewrite sine in terms of complex exponentials. So I'm going to call this whole thing u. So this is, well, maybe I should do that. I can call this k, sine of kx. That would be good enough. So I can rewrite sine as e to the plus ikx minus e to the minus ikx divided by 2. Now, why did I do that? I did that because if we're talking about momentum, then we want to write our wave function in terms of the eigenstates of the momentum operator, which are e to the ikx. So that what we just did, writing it this way right here, is writing our wave function in terms of those special states for that operator. Okay. So so this right here. Okay, so normally this example it's going to be a little weird in terms of normalization because the momentum eigenstates, remember, are non-normalizable. So there's kind of a separate issue going on here. But let me write this way. This is some constant times e to the plus ikx, and it's the same constant minus e to the minus ikx. Right. So these are two different functions. Let's call this one f plus. This is f plus of x. And this one is like f minus. This notation is maybe more confusing than it's worth. The point here is that this is the coefficient that is going to tell us the probability that we would measure this result. So remember, this function corresponds to a particle moving in the plus direction with wave number k. As long as this wave function is normalized, the sum of the squares of these constants would equal 1. Okay. So what we're saying here, the probability that you'll measure, say this result, is that you just take this coefficient and you square it. This gives you the probability that you would measure plus ikx over h bar. I guess oh no, for probability, or for, I guess I need an h bar here, don't I? Oh no, it's in the momentum operator. The better example is probably over here. Running into problems with this example because momentum is not normalizable. So I guess I'll just say that there's some normalization problem, but then this would be 1 over square root of 2 times a plus momentum eigenstate, and 1 over square root of 2 times the momentum eigenstate where the particle is moving in the negative direction. And so the fact that it's like 50%, if you measured the momentum, you would get, there's a 50% chance you would get the particle moving to the right. That's because this thing right here squared is 1/2. And to the left, this thing right here squared is 1/2. Okay. I kind of stuck a in there because to normalize the state. Let's look at another example where we the normalization is less of a problem. Okay. So this is a linear combination of two energy eigenstates. So you have psi2 and psi7, right? The n equals 2 state of the particle in a box and the n equals 7 state of the particle in a box. And so our psi of x is square root of 3 over 2 times psi2, and then minus 1 over 2 psi7. I just multiplied the 1/2 on both sides. Now, why is this factor of 1/2 here? This is so that this whole thing would be normalized. So actually, if you didn't have the 1/2 and you did integral of psi squared, and you normalized this whole wave function, you would see that you needed something of absolute value 1/2 in front. Okay, so if we have this state and we measure the energy of this state, what are the possibilities and with what probabilities? Well, we've written our wave function in terms of the eigenstates of the energy operator. So psi2 and psi7, we wrote our psi in terms of psi2 and psi7. In terms of all the psi-n's, so the coefficient in front of psi1 is 0, coefficient of psi3 is 0, psi4 is 0, etc. Now what we can do is read off from the coefficients squared right here. And this one has the minus sign, but you know, if you square the minus sign, it doesn't really matter. So this tells us this coefficient squared and this coefficient squared tell us two different things. This is the probability that we'd measure E2. And this is the probability that we would measure E7. And the probability that we'd measure any other energy would be 0, because you know this is like plus 0 times psi 5, for example. 0 times psi any other n value. So the probability we'd measure E2 is square root of 3 over 2 squared is 3/4. And the probability we'd measure E7 is 1/4. 1/2 squared is 1/4. And actually, it's knowing that these probabilities need to sum to 1 that I know that I have to put a 1/2 right there. So this is one question you could ask. Another question is, what is the expected value of the energy? Well, imagine you had 1 million copies of this system and you measured the energy. You know, there's a 3/4 chance you'd get E2, 1/4 chance you'd get E7. So actually, the expected value of energy would be 3/4 times E2 plus 1/4 times E7. So what this is saying is if you took this and you computed the expected value of the Hamiltonian, right? You did psi star, so you plug this whole thing. Imagine how complicated this would be, right? Because psi2 would be sine of 2 times pi times x over L. So you'd plug that in and you'd plug psi7. So you do psi star, the Hamiltonian operator, so kinetic plus the potential energy would be 0 here, and then psi. And you compute that whole integral, you would get the same number as this. Right? So this is a much more efficient way of doing that computation. Right? Okay. So we have a few clicker questions. Might as well go through these as more examples. E to the I kx is a stationary state wave function for a free particle in one dimension. Okay, right? Stationary state wave function, energy eigenstate. So if something's a momentum eigenstate, well, if a free particle is a momentum eigenstate, then it's definitely an energy eigenstate. Right? Careful, because we were saying in the particle in a box that the energy eigenstate was not necessarily a momentum eigenstate, but momentum eigenstate is a energy eigenstate, as long as the potential is not changing. Okay, so if the wave function was instead this, and as soon as you see, you know, e to the ikx and e to the minus ikx, this is the same thing as cosine kx. Let's see all these statements. The particle is still in a stationary state. So let's see, is it still an energy eigenstate? En energy eigenstate? The answer is yes. Right, so whether the particle has wave number k or minus k, whether it's moving in the plus or minus x direction, if the wave function is 50-50 between those two things, then, and they both have the same energy, you add them together, you still have a definite value for what the energy is of the particle. So the particle is still in a stationary state. Yes. Answer is yes. The expectation value of the momentum of the particle is 0. So again, because these coefficients in front of this and this are the same, there's a 50% chance the particle is moving in the plus x direction and 50% chance it's moving in the minus x direction. So the expectation value of the momentum is 0. That is true. The expectation value of the energy of the particle is 0. No. So the expected, it has a definite value, but that value is not 0. So the expected value of the Hamiltonian, or the energy of the state, because it's a free particle, this is the expected value of the kinetic energy, and this is h bar squared k squared over 2m. So we don't know whether the particle is moving in the plus or minus x direction, but we definitely know the magnitude of the wave number is k, and this would be the kinetic energy if that was the case. H bar squared k squared. This comes from p squared over 2m. It looks like 1 and 2 only for this one. All right, let's try another one. Choose all of the following statements that are correct. Number 1, the stationary states refer to the eigenstates of any operator corresponding to any physical observable. No. It was a struggle to read the rest of the sentence because it's not just any operator. This is the stationary states refer to the eigenstates of the energy operator. But the eigenstates of the energy operator are not the same as the eigenstates of other operators. For example, the position operator is going to completely collapse the wave function into an eigenstate of position. So, you know, if you started off with an energy eigenstate and I measured the position of the particle, all of a sudden this is going to be replaced with, oh, I measured the position to be right there. But then I have a momentum eigenstate after that. Or sorry, position eigenstate after that. And that actually has a lot of energy, right? In order to really localize a particle right there. So we've introduced a lot of energy into the system by trying to locate it. All right, number 2. In an isolated system, if a particle is in a position eigenstate, has a definite value of position at time t equals 0, the position of the particle is well defined at all times t greater than 0. No. So again, back to that example. So if this was our state, it requires, so if delta x is close to 0, now if we measured the position and we're pretty certain about where it is, then the delta k has to go to infinity because of the uncertainty principle that I talked about at the beginning of the video. But if there's a lot of uncertainty in the momentum, this particle is going to disperse. It's going to undergo dispersion. So this wave packet that's localized at the moment you measure it is going to spread out over time. So this is no longer a stationary state. It's not the probability density is not constant over time. It's just going to change over time. And in particular, it's for this very reason, it's going to disperse. And the final question, in an isolated system, if a in an isolated system, if a system is in an energy eigenstate at time t equals 0, the energy of the particle is well defined at all times t greater than 0. The answer is yes. This one isn't quite so obvious. This is maybe outside the realm of what we want to talk about here. This has to do with the time dependent Schrodinger equation, right? The time evolution. And the time, what's going to happen at time t greater than 0 follows the time dependent Schrodinger equation. And the time dependent Schrodinger equation is a statement of conservation of energy. So the energy is going to be conserved as long as the system is isolated. So it looks like this is okay. And that's okay, because there's no option for all three are bad. So it looks like 3 ohm. And that's all we needed to talk about. So this video was probably more info than we need in this class. I just wanted to I wanted to give you a sense of what measurement is all about in quantum mechanics. And obviously this is very complicated. There's a lot to this. But the key takeaway message here is that if you're measuring a fuzzy observable, if you have an operator and you have a wave function where that observable is fuzzy, and then once you measure that quantity, you've changed the wave function. And if your wave function is sharp in the observable and you measure that observable, you're not going to change the wave function. You're just going to get back the value that you already know 100% what it's going to be. That's the gist of it. And it's the coefficient squared that you write your wave function in terms of those eigenstates of your measurement operator. The coefficient squared tells you the probability. That's the key here. I think just going by this example and applying it is enough to do your homework problem. Okay, please ask questions on Piazza if you have any questions about any of this.